In Battery 101, Part 1, we discuss batteries and their construction. In this article on batteries, which is the second of a two-part series, we're going to be discussing battery selection based on their job once installed. First up, we're going to be discussing starting batteries. As mentioned earlier, starting batteries are less heavily constructed than deep cycle batteries for one simple reason. They can be. Deep cycle batteries have to supply relatively small amounts of current over an extended period of time, while starting batteries are required to supply a large amount of current for brief periods, normally about 5 seconds. That's where the difference begins. Starting batteries are constructed of thinner, more numerous plates, a design that maximizes surface area and provides the highest burst of current possible, exactly what's needed for cranking an engine. Deep cycle batteries have the thicker, and by default fewer, plates required to survive prolonged discharges. However, this reduced surface area provides less cranking power, which is why deep cycle batteries have to be oversized when used for starting. What starting batteries are not designed to do is to be deeply discharged. This isn't a problem under normal use, as only a small amount of the battery's actual capacity is used while starting, and that's quickly replaced by the alternator once the engine is running. The thing to remember is that they work just fine when asked to do the job they were designed for, that of cranking the engine. The problems start when they're forced to work as a deep cycle battery and are subjected to the deep discharges associated with them, which causes their thinner plates to buckle and fail rapidly. Even the hardiest starting batteries fail after 15 or so deep discharge cycles, with many self-destructing in as little as 3 or 4. So what should the average boater carry away from this? Well, for starters, my one pun for this article, the realization that standard automotive batteries should be eliminated from all but the most perfunctory applications on board. I know they're cheap and you can pretty much get them anywhere, but despite the similarities in appearance to real marine starting batteries and that heavy-duty label, they're just not built to stand up to the marine environment. Keep them under the hood of your car or truck where they can lead a safe, productive life without causing undue headaches and grief on the water. Deep cycle batteries. Deep cycle is a term chronically misused by battery manufacturers as a sales buzzword to imply a more heavy-duty product. Although any battery can technically be termed a deep cycle, as all can be deeply discharged and recharged, only a true deep cycle battery is designed to withstand such discharges time and time again without premature failure. Cheaper substitutes can suffer irreversible damage after only a few such deep discharge cycles. A true top-of-the-line deep cycle battery has solid lead plates, allowing hundreds of deep discharges up to 80% with no significant reduction in projected service life. Thicker plates are the key to withstanding these deeper discharges, which is why premium deep cycle batteries weigh and cost as much as they do. The reason plate thickness is so critical is due to something called positive grid corrosion, a key factor in battery failure. The positive plates of a battery are eventually eaten away over its service life, meaning all things being equal, the thicker the plates, the longer the battery will last. Unfortunately, most deep cycle marine batteries on the market today utilize lead sponge plates rather than solid lead. These are heavier than what you'd find in a starting battery, but lighter than those of a true deep cycle battery. Golf cart batteries are a popular choice with many boaters from both an economical and reliability standpoint. Although actually a semi-deep cycle battery, they're designed to provide moderate current output for extended periods of time and will outperform any starting battery and most available marine batteries for that matter, but not a true deep cycle battery with solid lead plate. Heavy means more lead, and weight is good as far as batteries are concerned. True deep cycle batteries can be used for both deep cycle and starting, while starting batteries will exhibit poor cycle life in deep cycle applications. When using a deep cycle battery for starting, the general consensus is that it should be 20 to 25% larger than the existing or recommended starting battery in order to provide the required cranking amps. A good oversized deep cycle battery is a better option, in my opinion, than one of those hybrid combination batteries where manufacturers produce this battery they claim can straddle the gap between cranking and deep cycle applications. Some advocates say they're fine for the weekend boater who spends an occasional night away from the dock and his shore power, but how can they meet both the thin plate requirement for a true starting battery and survive the deep discharges that necessitate thicker plates? It's like trying to please folks who like orange juice and sauerkraut by combining the two. The end result is a product combining the limitations of both with the inability to meet the needs of either satisfactorily. An oversized deep cycle battery, especially in single battery applications, also increases deep cycle performance for all the power sucking must have electrical doodads that invariably find their way on board. Additionally, advances such as fuel injection and electronic ignitions have reduced the number of raw cranking amps a battery has to provide anyway, making the deep cycle option even more attractive. The only real caveat I can think of for using deep cycle for cranking might be the need to monitor the battery's state of charge a bit more closely, especially when the engine is started frequently but ran for only short periods of time. Due to design and heavier construction, a deep cycle battery takes significantly longer to fully charge than a starter battery, meaning they may require additional charging in the above scenario. Section E10 of the American Boat and Yacht Council, Standards and Technical Information Reports for Small Craft, covers battery installation requirements in great detail. But we'll touch on the basics here, which are generally the same for all battery types, wet cell, gel cell, or AGM, absorbed glass mat. First off, ABYC requires that all batteries be installed in liquid-tight, acid-proof battery trays or boxes. These are available commercially at most marine supply outlets. However, you can make your own as long as they meet the above requirements. Just make sure that the mounting hardware, the bolts and the screws and such, don't compromise the leak-proof quality of the containers. One thing when you're making these containers or buying the trays or boxes, they do not have to be of a sufficient capacity to hold all of the battery electrolyte, only the amount that may boil over or leak out. Batteries are also required to be secured against movement, 1 inch max in any direction for at least 1 minute, when exposed to 90 pounds of pull or twice the weight of the battery, whichever is less. E10 also requires positive terminals to be covered to prevent accidental shorting from dropped tools, for example, a requirement that can be satisfied by the use of rubber or plastic terminal caps or boots, non-conductive covers, or by the lid of a battery box itself. While batteries should ideally be located in a cool, well-ventilated area, excessive heat can significantly reduce battery life. Many installations place them in the worst possible area in this regard, the engine compartment. If that's the case on your vessel, the best location is usually low in the engine room, but well above the normal accumulation of bilge water, which typically keeps them away from mufflers or exhaust manifolds, while hopefully providing some benefit from the existing engine room ventilation. Adequate ventilation is critical to remove fumes and gases generated while charging. ABYC recommends chargers or other electronics never be installed directly above a battery, as they could be damaged by these corrosive vapors. Other installation problems involve fuel system components. Never install batteries above or below fuel tanks, fuel filters, fuel line fittings, or similar fuel system components. Installation above or below an uninterrupted one-piece non-metallic fuel line is okay. However, any metallic part of the fuel system within 12 inches of a battery terminal must be shielded to prevent sparks. The exact shape of this 12-inch exclusion zone varies slightly between side and top-mounted battery terminals. You want to reference ABYC E10 for the specifics. However, in general, if you can touch both the fuel system component and battery terminal with a 12-inch piece of string, keeping the string taut, it has to be insulated. It's also worth noting that the presence of terminal boots or battery box lids do not fill this requirement, as they're usually removed while servicing the battery. The time sparks are most likely to be generated. Finally, E10 requires battery terminal connections to provide secure mechanical and electrical connections. Spring clips, alligator clamps, and the like are not permitted. The use of wing nuts is also discouraged, as it's difficult to apply enough torque to keep them from loosening. And in my experience, eventually they loosen due to movement of the boat and vibration, and they come loose. So My personal advice, is to remove all of your wing nuts on these primary battery terminal connections and replace them with stainless steel nylock nuts. Death of a battery. While each battery type has their pros and cons, wet cells are the cheapest but require routine maintenance. Gel cells are maintenance free but are more costly. AGMs are robust enough to survive installations that would literally shake a wet cell battery to pieces, but twice the cost. They all work well if properly installed and maintained. Regardless of which you choose, premature failure is not the normal part of the circle of life, and almost always results from abusive practices or failure to respect construction limitations of the battery itself, typically in the form of poor charging methods or deeper than recommended discharges. If you're not getting 4 to 6 years out of a good set of marine-grade batteries, it's time to step back and see if your battery maintenance philosophy addresses the primary causes of early battery death. First up, sulfation, the silent killer. Each time your battery discharges, soft lead material forms on its plates, a process known as sulfation. Lead sulfate acts as an insulator. Current doesn't flow well through it, and as the accumulation of the plates increase, battery voltage decreases. The good news is sulfation is a normal result of the charge and discharge cycle and is reversed during recharge. This process is not 100% efficient, however, meaning a small amount of sulfate remains on the plates after each charge and discharge cycle. This residual sulfate, while unavoidable, is expected and not a major cause of battery failure. The real problem begins when batteries are left in a discharged state, at which point the lead sulfate begins to harden and crystallize, forming a permanent insulating barrier that can't be removed during normal recharging. Deeper discharges and longer periods between recharges mean increased levels of sulfation, which reduces the battery's ability to charge or discharge, dooming it to an early failure. One reason depleted batteries must be recharged as soon as possible. Other factors affecting battery life: depth of discharge, rate of recharge, and heat. Batteries discharged within the manufacturer's recommendations, typically around 30% of total capacity for wet cell batteries, will last substantially longer than those subjected to discharges deeper than 50%. This recommended maximum depth of discharge can vary greatly between battery types. AGMs can be discharged to a depth of 20% without harm, a key selling point in some cases, as long as they're not subjected to overcharging at higher than recommended voltages. The problem with extreme discharges is that each time it occurs, some of the active material on the battery plates is sloughed off, falling to the bottom of the battery or accumulating between its plates. This cast-off material eventually shorts out the cells, resulting in battery failure. The key to avoiding problems associated with extreme discharge is selecting batteries large enough to meet normal energy requirements while staying within the recommended percentage of discharge. Externally generated heat from engines, engine exhaust systems, or even vessel location, tropical latitudes for example, can also reduce battery life, but internal heat generated while charging can damage batteries as well. Let's talk about battery charging. Battery charging 101. All battery installations require some method of recharging batteries and keeping them topped off, a need typically satisfied by either the engine alternator or, in the case of vessels docked or having AC generators on board, an AC-powered battery charger. Boaters relying solely on alternators, however, particularly sailboats, may be slowly killing their batteries. Many vessels carry multiple banks of large, oversized batteries to provide power while away from the dock. In such cases, unless the owner has upgraded their conventional alternator with a high output model, chances are these batteries never get fully recharged, typically only to around 80 to 90% of capacity, due to the additional engine running time required for lower output alternators to fully charge them. A situation leading to increased sulfation, as it's the last bit of hard charging that helps reduce sulfate accumulation. Most battery installations rely on AC-powered chargers to pump in that last 10 to 20% of charge. Probably the worst thing you can do after carefully selecting a battery is to swing by Bubba's bait shop and grab the first charger you see. Chargers have to be matched to your battery's construction and capacity for maximum service life. Too large a charger can cause battery overheating, while one that's too small can result in excessive sulfation. How battery chargers work. Traditional ferroresonance chargers combine a constant voltage source with tapered charge characteristics and are based on the differences between charging and voltage battery terminal voltage. As battery voltage increases during recharge, charge current decreases. Charge control in more advanced ferroresonance chargers is typically via a sensing circuit or regulator, which either turns off the charger when a preset voltage level is reached or reduces charger output to a float voltage of around 13.8 to 13.5 volts, depending on battery type, once the battery is fully charged. The problems with ferroresonance chargers include generation of high AC ripple, which can also cause internal heating of the battery while charging, and the fact that not all ferroresonance chargers are properly regulated. If the float charge mentioned above remains at the higher charge rate, 14 volts DC or greater, battery electrolyte will eventually boil off or evaporate and need replacing. With wet cell batteries, this means you simply have to top off the electrolyte more often, but in the case of sealed maintenance-free batteries, permanent damage results. In contrast to the above, newer smart chargers divide battery charging into 3 stages: bulk, absorption, and float. This controlled multi-phase approach to charging is both more efficient and battery friendly. All battery types charge faster and last longer when charged in distinctive phases, particularly when the charger has multiple settings, as all the better ones do, allowing you to select specific battery types to be charged. The other major benefit of this newer technology is that it allows boaters to purchase a battery charger that can be installed and operationally forgotten, all the while keeping your batteries in top condition. Here's how they do it. The bulk stage. This initial stage charges the battery up to 75% of capacity utilizing a limited controlled high charge current, typically around 30% of the battery's capacity in amp hours. A max of around 14.4 volts for wet cells, 14.2 for gel cells. This controlled use of high charge current both charges the battery quicker and protects it from the damaging effects of excessive high internal charge current and the heat it generates, produced by older chargers. Absorption stage. Once the battery is around 3/4 charged, the absorption stage kicks in, charging the remaining 25% of capacity. Max charge voltages mentioned above remain steady while amperage is slowly reduced until the battery is fully charged. Then we have the float stage. During the float stage charge, voltage drops to 13.5 volts, 13.8 for gel cells, which is below the gassing point, reducing electrolyte loss, but high enough to maintain the battery at full potential for extended periods. Some chargers include a 4th equalization stage, which is essentially a manually controlled overcharge condition aimed at dissolving residual sulfate left on the battery's plates after the normal charge cycle is complete. One important thing to remember, equalization applies to wet cell batteries only, and if required must be done with care to avoid battery damage. Following all manufacturer's instructions while closely monitoring both electrolyte levels and the specific gravity of each battery cell. It's also important to verify all applicable battery system components, wiring for example, is sufficiently robust to handle the equalization charge, which typically peaks at around 16 volts. Charging multiple battery banks. Although most vessels typically have a single permanently installed charger on board to take care of their charging needs, for best results, those with multiple house banks or twin engines with separate batteries should ideally have separate charging systems or a means of splitting the charge to each battery or bank. Newer chargers offer multiple outlets, providing isolated charging outputs for each battery bank. Efficient multi-bank charging only occurs when the batteries comprising each bank are of the same size, type, and age. Duty cycles should also be closely matched. If a battery bank consists of different sized batteries, the smaller will invariably be overcharged, while the larger battery will suffer from chronic undercharging, both of which cause premature battery failure. Finally, when replacing a defective battery that's part of a battery bank, i.e. one connected in series parallel with one or more other batteries, the replacement battery should ideally be of the same age and condition as the remaining batteries in that particular bank. For best results, install a good used battery matching the others. or simply replace the entire bank with new ones. And although it goes without saying, I'm going to say it anyway, make sure that the battery is of the same type of the one that you're replacing. In other words, if you have a battery bank with wet cells, don't replace a defective battery with an AGM or a gel cell. All of your batteries, particularly the batteries in the same bank, should be of the same type. All wet cell, all AGM, or all gels. A common problem I see during surveys is a owner that has, let's say he has a wet cell battery for his engine start, and then for his house bank batteries, he's got AGMs. But he only has one charger charging everything. Well, the problem with that is that unless the battery charger has the capability to charge different types of batteries, in other words, it has one leg can charge AGM and the other leg can charge wet cell. One of those batteries, or one of those types, either the wet cell or the AGM, are not going to be charged at the proper voltage because they have different ideal charge voltages. So, in a perfect world, you keep all of your batteries of the same type, and then you don't have to worry about overcharging or undercharging the batteries.